Hello, everyone.
Hi, everybody.
Hi, Markus.
New faces today. Awesome.
Hi, Markus.
Hey everyone.
Hello.
Hello.
I suggest we just give people
Nice to meet you.
maybe 2 more minutes arrive.
Okay. We have some slides. We can actually basically get it prepared.
Andrew. So you were saying you're going to present today?
I thought we are supposed to present like Marcus, I think, is in the call. He invited us to talk about the Specula kind of tool.
Okay.
Yeah, today basically.
Yep.
Good.
Amanda and Taylor figured out the logistics with you, right?
Hey, everybody. Good morning. Good evening.
Good to see you. Okay, shall we get started? So, yeah, if you have stuff to present, why don't you just go ahead? I mean, if you want to share your slides or whatever.
Sure. We can try. So let me try. Are you able to see the slides?
Yep.
Yes.
Good.
Or only have one screen, so like let me adjust a bit my screen so I can see my slides also. All right.
Okay, so just fire off whenever you're ready.
Oh, sure, yeah. I can do it at any time. So like, do you want to actually start now, or like this is my first time like attending the community meeting. Like, I actually don't really know how the format is supposed to be.
Yeah,
And
so usually we have a round table kind of where everybody says, well, what he or she's been doing. But I mean, if you have something to present, why don't we just start with that and
sure,
have
sure.
our
Like,
round table later.
so first of all,
If I
like, thank
may-
you for. Yeah, go ahead, Marcus.
Quick framing here. So this is the first presentation that sort of comes out of the TLA Plus Gen AI challenge that we ran earlier this year. This is the first place submission, and I asked the Specula team to present their solution, which I think is pretty great work here at this community event. So please go ahead.
Thanks, Marcus. Again, like, thank you for even organizing the challenge. And like you can see, like we have a very big team, very strong team, and amazingly, like all of us is actually like in the call. So like you can see, Ivan, you, like Rachel, like Emily, Yiming, like in the call. So like this tool was actually originally created like for this challenge, and thank you for the recognition, and also for the GPU. Now, like we actually have like a much stronger team. We actually did a bunch of things after the original tool. So like I'm going to like briefly talk about it. Like here, like we have like 4 institutes, like Nanjing University, Microsoft Research, University of British Columbia, and UIUC. Like so today, like Chen, Emily, and I, like basically going to tell you like a bit about like what is actually our vision, how much like progress we have been making, like basically these days. So like let me very briefly talk a little bit about how like some of us actually get started, like even like using TLA to do some model checking for some like real world like basically systems, right? Like we actually started like this project trying to like basically verify Apache Zookeeper like basically 5 years ago, actually even longer. So for those of you who actually know Zookeeper, like from the Hadoop like time, right? So it is like basically one of the most important piece in the whole like Hadoop stack, right? Because it actually provided you this like coordination service. If you want consensus like services, like that's like basically the system you use. Almost like every fault tolerant component like in Hadoop like basically using Zookeeper for that. So like the core like to Zookeeper implementation is actually like the implementation of this distributed system protocol called the ZAB, which stands for like Zookeeper Atomic Broadcast. So if you are not like basically familiar with ZAB, it's no problem. Like it's basically you can think about it as a Zookeeper specific like basically Raft or Paxos. If you are like more familiar with Paxos or Raft. And here is like basically the figure like which shows like the high level idea of the ZAB protocol from the original paper, right? Like you can see there are 3 phases: discovery, synchronization, broadcast, and it's actually leader based protocol. Like so any like failures of the leader or the follower like will be tolerated. So since like our goal is actually to to actually verify the implementation of the ZAB. So like one thing like we basically have actually like from the previous slides, we all like know like how great TLA Plus is. Like you can actually find the TLA Plus specification for the protocol like even in the Zookeeper's open source repository. But the one like since like we want to actually verify the implementation, right, the code, soon like we're just realizing that like the protocol like specification is not actually sufficient. Like for a number of reasons. Like here I list 2 reasons. For example, like in the protocol specification, it does not actually describe like some of the system level optimizations, right? For example, for performance. For example, like one atomic action in ZAB is often like implemented by several concurrent operations in Zookeeper, right? Like in the code for performance, because concurrency means performance. But actually, like the protocol, like because they don't really describe that, like they cannot actually address any concurrency bugs like in those code. Also, like more interestingly, like ZAB, like as a protocol, they don't really describe the leader election process, right? Like it happen to be like leader election is one of the most complicated like an operation in the Zookeeper implementation, right? It has its own name called FLE, like fast leader election. So if you don't describe it, like in the protocol, like it's basically an oracle. Then like the protocol specification cannot actually address any like basic bugs in the FLE component. So that like basically like leaders like want like have a different specification, which is actually we call them system specification. And the system specification like is supposed to describe fairly well like about the code implementation, not only like the protocol, right? So the process like we actually went through is that given like the system code here is actually like the Zookeeper's implementation of ZAP. We want to write like a TLA plus system specification, which actually like effectively describe some of the behavior of the system code. For example, like in concurrency, right? And when we write it, like one thing we try very hard, like many of us like try very hard, is try to like conform that like the system specification actually like is conform like to the system code, like using trace validation. Marcus did a lot of work, like and we actually also like did some work like basically in different systems, try to making sure like these two things they conform to each other, right? And once like we have a good like system specification, we can like basically feed it into the TRC model checker, like check like basically against all the environments we want, right? Like in terms of like safety and liveness. And either like we are able to like verify the implementation like with some confidence, or like we're going to find some bugs and fix them. So far so good. One thing like to note that like by writer specification, like I actually mean handwriting specifications. I basically mean like the grad students like handwriting like specification like very like working very hard on that, right? And some of them like actually like in this call. And one thing like probably like you already realize like since you actually like know like very well about TLA plus is that if we actually describe like if we write a specification which describes some low-level details, we're soon going to like basically hitting this problem called the state like space explosion, right? Because like it's too low level like then like the model checking never finish. So to solve that problem, like we actually like basically designed some approach. We call it like a multi-grand system specification, and the idea is like trying to write multiple specifications like of different components of the system, right? So in the ZAB implementation, like in Zookeeper, like we actually divide the components into based on their phases into like these four: election, discovery, synchronization, and broadcast, right? And for each component, like we write multiple specifications in different like granularities, right? Like from the very high like basically level like granularity to very low level granularity. So why I want to do that? Because usually like when the code evolves, it doesn't like we don't really change everything like at once, right? We're changing like sometimes only a part of the component. Let's say like we're now like only changing like the component of the sync. Then like we can actually compose a mixed grand like system specification, which compose like basically some high level specifications of the unchanged code, right? Like they are already verified, they are never changed, so we just like using them. And for the one like we change, we actually use like the most detailed specification like we write, which describe like some of the low-level details we want to verify. And of course, like we also do like the conformance checking like before, and then like we play the old tricks, right? Like either find some bugs or verify some like the implementation. But if you think about it, like it's a lot of efforts in writing specifications, right? Now, not only like we write one, like we write actually multiple. In like in our paper, like we actually write 3. Like this paper is at yours. If you're interested, like check it out. Like when like I find like it's great work. Like actually it's published at top conferences. It's literally like 5 years of a PhD student work. Actually, I put 4 years yesterday, but Rita told me like literally I spent more than 5 years. Right, it's a lot of like time. Very like brilliant grad students like actually spend in their life. And why like they spend so much time, like I believe like everyone like have this experience. Like for this project, the student has to actually read and understand Zookeeper code by heart, right? Like if you want to write a system specification, you better like know very well about implementation. Student has to learn TLA plus. Unfortunately, like I think none of the like universities like we have like actually teach TLA plus in their basic undergraduate like curriculum, right? So students has to actually like spend like additional efforts like try to learn TLA plus and like learn languages like the mechanism, like reading like the Lamport book and all these things. And after that, like they have to write at least one TLA system spec, right? Like like basically, which is actually like basically interesting and high quality. And after that, like as I mentioned, they have to write like multiple TLA like system specification. Not only that, like because we want to check multiple versions, like to actually like needs to maintain like the TLA specifications for different versions, right? It's just a huge amount of work. If you agree with me, it actually take like 5 years of a PhD student, and it's not only take like 5 years of one PhD student, but like 5 years of n PhD student, because we actually did like a number of projects, right? Razor is in the code. Like after this project, he actually did kind of the same thing, like with some like very interesting optimizations for like basically the synchronization primitives, like in the Astorianus like operating system kernel, right? The work is actually published also like in this year. So the real like basically thing like we hope to like basically realize the promises is that can we just turn like this 5 years of a PhD student life into like 5 ARM course, right? Like things like these days like everyone is crazy about those models. And I actually like truly believe like we can like realize that, like probably not now, like but in the very near future. Because if we like reason about like the time like our students actually spend, you may realize that like some of them are kind of already like realized like by the like basically the power like of the AI models these days, or like the AI agents these days, right? For example, like Zookeeper code is already like in the training set of all the coding models these days. Like I'm actually like very interested to learn like the markets like kind of like the TLA like the benchmark, like to know like how much like basically the models know how to write TLA. But at least like when we try like our stuff, like we find that it actually knows something about TLA, like we can actually make it stronger. But like there is a hope. So the focus like of the project is trying to like actually on the third bullet, right? Like can we just write one very high quality TLA plus system specification we're all proud of, like we're actually like happy to use in our own like research projects to try to find bugs and like verify the system code. That's like the goal. And if we can do that, like what we believe is that the next two like are more or less like solvable, right? Because it's more like kind of applying like the same technique like to like just to tell like the model or the agent like what are the granularity we want, and then like they should be able to generate, and then I can apply it like into different versions, or hopefully every single version. So like ideally like here is our like basically vision, like if you want to call it a vision, like we basically want feed like some models like all the agent, right? Like basically the system code. Hopefully like the Zookeeper is like an implementation of that, but like Zookeeper is a last generation systems, like now like everyone like moving to cloud native systems, like we're actually like looking at XCD, right? Like which is this key like service similar to Zookeeper, like but in Kubernetes ecosystem. And our hope is that like the agent like is going to like query some models, like using some tools, including some static analysis tools, like basically like model checking tools, like all conformance, like checkers, which we haven't like integrated. That's why it's a dotted line. And then like producing like very good like high quality TLA plus like system spec for us. That's like what we hope. Like we like like personally like I didn't really know like about AI like 6 months ago, and I thought like okay, like this is should be like somewhat like already realized, but actually like it's not really. Like we tried like basically on the state of the art AI and agent LRMs and agent, and we found like it's actually not satisfying. Like and to prove like this point, we actually built a benchmark. The paper is actually on arXiv. You can find it. So like essentially the benchmark trying to automatically evaluate the quality like of a given TLA plus model, right? Like so we ask like basically the state of the art like AI agent to generate a TLA plus model, and then like we are going to evaluate like how great like this model is, and we have like basically 4 criteria, right? Like here, like from the very basic, like we just want to know whether like the model is able to get the syntax right. To like basically when you get a model, like whether it actually can run, like does it like actually throw like runtime errors, right? And if you can do these 2 things, like then like the very important question is that does like this model actually describe the system's code, right? Because like that's what we want. If the model does not really describe the system code, then like it's not very useful for us to verify like the system. And lastly, like basically whether like this model actually satisfies like all the invariants we are expecting. And if honestly, like if it satisfies like the 3 boxes before, then like it basically means like if it fails the invariants, we even find a bug. But actually, the reality is that like it don't really like do very well, right? Here is the good news and bad news. We tried like I think like basically 9 systems, including like the Pico system like Ivan has been building at UBC, and there are a lot of interesting results like we find in the process. But here is like the very like basically first result. We tried. The good news is that like for the simple system, right? Spinlock is actually the simplest system we basically like tried. Like in the entire benchmark, like it's actually a real Spinlock implementation, like from Astorianus, like an operating system kernel. And everyone knows the Spinlock like concept, and you can see that like the agent actually like it's a very basic agent which just prompting models, like it does actually fairly well, right? Like, it's very reasonable, especially for some strong, like, coding model like Cloud. But for more complicated system like a Raft, right? Like, the Raft implementation, like, in XCD, it's doing like pretty poorly, right? The strongest model like a Cloud, like, can get the syntax right, but like, it cannot barely like generating a model like, which actually like, can run without any runtime errors, and not to mention conformance, right? Like, only very low, like, percentage numbers. So that basically, like, really, like, kind of hopefully, like, motivates you that, like, we actually need, like, some smart solutions, which, like, just doing, like, more than like just prompting the LLMs, right? So Emily is going to like tell us about this, like, basically tool we built called the Specula. One thing, like, before I hand to Emily, is that, like, actually everything, like, about Specula, its code, and also like the demo code, like, here, like, we are presenting today, is actually on GitHub online. Like, so I would highly encourage everyone to try it out and give us like some feedback. And here's like, we have like a group of people like who are very serious about actually building it right. So Emily, like, do you want to present the tool? I can actually like basically play the slides for you, like, if it actually saves some of the handoffs.
Yeah, sounds good. So yeah, with those benchmark results in mind, we see that the LLMs, the raw LLMs, aren't performing very well. So we wanted to see how they might perform beyond basic prompting. So this is why we built Specula, which is an open source framework that takes the source code of these real-world distributed systems and generates these end-to-end specifications with a pipeline of specialized tools. Again, yeah, you can check it out at github.com/specula-org/specula. Specula uniquely leverages these LLMs' code translation capabilities to handle these complex systems. Because translating code is easier than comprehending the system architecture, we can view spec generation as this translation from the code base to TLA+. Specula takes a sort of neurosymbolic approach here, combining these large language models with more grounded symbolic reasoning. For example, we've built a TLA plus control flow analysis tool to help statically tweak these generated specs so we can enforce constraints like single assignments, maintain these unchanged variable lists, and annotate these updated state variables. And we saw previously in those benchmark results that these raw LLMs struggle to even generate syntactically valid TLA plus. So Specula iteratively autocorrects its own errors. It incorporates feedback from existing tools like SANI, TLC, trace validation. And we've also built a retrieval augmented generation pipeline that takes common syntax errors and their fixes and helps to guide the corrections for the model. And this iteration also allows for interactive human-in-the-loop usage. And next slide, please. So we can now get a quick overview of Specula's design before getting into a demo. Specula will take in the system source code as input, and its first phase, this generator, performs a raw translation from code to TLA+. This will keep a mapping between the code functions and the spec actions to prevent the LLM from inventing logic. Next, this initial generated spec might have some syntax issues, so we proceed to this quick syntax correction loop using that like autocorrection we talked about previously. After syntax errors have been fixed, the next step is control flow analysis. Even though the spec is syntactically correct at this point, this direct translation preserves a lot of code control flow patterns that don't make sense in TLA+. So we will statically fix these issues with our control flow analysis tool. Next, at this point, our spec is free of code level patterns and it's syntactically valid, but we also want to model check it. So we run TLC on it, and we then use the LLM to generate a TLA plus config file, then start this iterative loop of running TLC and then auto-correcting any runtime errors. Finally, to ensure the spec conforms to the underlying system, we use trace validation to compare an instrumented runtime execution with the specifications actions and the state in TLA+. So the final spec will be both internally consistent, which will pass syntax and TLC checks, and also externally consistent with the system after passing conformance checks with the traces. And I'll now hand it off to Chen to walk through a demo of this 4-step pipeline.
Okay. Okay, hello everyone. I'm Chen, and let me share screen and show the Specula demo. Can you stop
Chen,
sharing?
probably like you can tell a little bit about the high level thing. Like I think here like what we want to show you to the demo is that we're using like the XCD like Raft as a target system artifact, right? Like as I mentioned, basically
Okay.
it's actually the hardest one, in our benchmark, which was not doing very well, by the state-of-the-art agent. So Chen is going to show us basically the process of basically using Specula to generate the XCD graphs TLA plus spec. It's actually currently using as a tool as a human assisting process Chen will actually demonstrate to everyone. So in the benchmark we never even touch the process by the Specula but here we will actually try to correct some errors as a human using tool. So the code is actually online. So now Chen is going to show his screen.
Yeah. Can you see the screen and hear me?
Yes.
Yes.
Okay. I will show Specula's four-step workflow takes system source code and generates a specification that is guaranteed to be consistent with your implementation. I will now demonstrate this workflow with the hardest case study of the etcd raft implementation. etcd is a popular distributed key-value store. Okay, let's begin with step 1, call to spec translation. And here is the result we pre-generated to save time. In the normal run, it may take about 5 to 10 minutes to generate this draft. This file is a high-level draft that Specula has uses large language model to first analyze the source code and generate. It outlines the functions at different levels of abstraction. Next, we will use Specula to let the large language models use this draft as a guide to translate the source code into a TLA plus specification. And this is a specification pre-generated. This translation creates a direct one-to-one mapping between functions in the code and actions in the spec. Importantly, this prevents the large language models from inventing logic and simplifies the code instrumentation in a later step. Let's compare this specification. And as you can see, it has a few syntax errors. Here, in this example, we see that we are missing an else branch. This is a common mistake made by large language models because they lack domain-specific knowledge. The model produces an if-then structure that is common in high-level programming language. But in TLA+, an else branch is required. And as you can see, this error message here is not closely related to the real issues and can even mislead the model. Therefore, expert-guided knowledge is necessary. We can use Specula to correct it, and Specula uses a retrieval-augmented generation process. We have manually built a knowledge base of like this of common TLA plus errors and expert solution. And here is an example. Specula queries this database, iterating on the fixes until we have a specification without syntax error. And to save time, here is a example at pre-run, a common at pre-run. And let's check the results. And as you can see in the results, large language model added the else branch. And at this point, Specula has now produced a translated spec in TLA plus with no syntax error. This brings us to step 2, TLA plus specification transformation. Even though this specification has no syntax error, it may have some high-level issues. For example, variables being assigned multiple times within a single actions. As you can see in this action, this variable was granted has already been updated. And later, in this branch, become follower. It updates the variable was granted again. And in this situation, TLC will silently skip that branch. Issues like this are difficult for both large language models and even experts to identify. Let me show you how Specula solve these issues. In simple terms, we use 3 new variables to break an non-atomic actions into several smaller actions. replacing one non-atomic actions with a sequence of atomic actions. We built this tool based on the TLA SANI to create the control flow graph. As a result, our control flow analysis tool is directly usable with any TLA plus specification. Let's check the result. And as you can see, in the same action and in the same branch, this time the processed branch no longer called the action directly. Instead, it set PC to another actions. And in these actions, it will call become follower. At the same time, TLC requires adding unchanged statements like this for all variables that are not modified. Our tools analyze for each actions and each branch the site of variable being modified and automatically insert the unchanged statement without any manual efforts like this, which large language models are not able to handle reliably. By the way, our tool is still under development and it not support synthesizing init and the next action. So let me use a version I prepared in advance. As you can see, and now at this point, we have a specification that is free of code level control flow patterns and interpretable by the TLC model checker. This brings us to checking and automated reflection. This step is similar to step 1, so we won't spend too much time on it. First, large language model will large language model will generate a TLA plus CFG file like this, which defines the specification and the constants. Then we can begin an iterative process of model checking with TLC and debugging. To save time, we let TLC run only 10 seconds and stop. If no error appears within that window, we treat it as a pass. At this point, we have a specification that can do model checking. Finally, Specula guarantees the specification conforms to the code. We use a trace validation framework to prove this conformance. Let's run the comment. First, using the one-to-one mapping established in step 1, Specula automatically instruments the source code. This allows us to capture an execution trace like this, which reflects the system actual behavior. And here is an example of the inserted instrumentation. You can see that the hooks are automatically placed at the beginning of the function. We then run a 3-node cluster and print out the collected traces. Like this. These traces record the sequence of function calls and the state of each node, exactly the information we need for model checking comparison. Finally, we execute the generated file with TLC to validate the system's behavior against the specification. As you can see, the freshly generated spec fills the check, which is expected. In the current version, humans still resolve this mismatch manually. Here, we have a corrected version. When TLC finishes without error, the comparison succeeds. At this point, we get a high-quality specification that is consistent with the real system. And the rough case study took about 1.5 hours total to generate, including about 1 hour of manual time fixing up trace validation instrumentation. Specula is also cost-efficient. On a full run with CloudOps and Cloud Sonnet, the final spec was generated for about $3.50 in US dollars. Now, that's all. Now we have seen how Specula works. Professor Xu will share a bit more about our results.
I thought you are going to share the results, but it's fine. Like I can share.
Oh,
Yeah, you can talk about your results. Let's go to the next. I hope you can see my screen. All right. Chen, do you want to talk about the results? Well, okay.
I haven't prepared. Can you talk about?
Oh, okay, sure. Yeah, like I mean, like the results is actually simple. Like if you look at the screen, like we actually we have 3 agents. The one called the basic agent is actually the one we use in the benchmarking, right? Like there's not much magic there. We're just using the agent to prompt basically the LLM, and it was doing poorly. So the number is exactly the same as the previous slide like you saw. Specula is just one which actually do a number of interesting tricks thanks to all the students' hard work, and you can see it actually lifts the results quite a lot, right? We also have other basically agents which doing trace learning. For those of you who actually kind of know the concept of learning automata from traces, that's basically the agent is trying to do. And right now it's actually not basically if we only apply the basic approach, it's not doing very well. Like kind of the slide shows that Specula kind of how to say outperform the state of the art AI agents without any additional basically accommodation for the TLA plus stuff. So let me discuss a little bit about some of the high level observations. And I hope basically at this point you are convinced that the LLMs or AI agents they can actually model some simple systems like a spin lock, but they are quite limited in comprehending complex ones like in Raft, right? Again, I'd love to talk to the community to see how well actually it's on the actual TLA plus side and how much it's actually at the system comprehension side. Conformance checking is critically important. No matter for benchmarking or for the tool, right? For benchmarking one thing we kind of basically constantly observe is that the models, the LLMs, they will try to memorizing the TLA spec in their training set, and they will come up with some specifications which is actually correct, but don't really describe the system we want to verify, right? And then that's basically the conformance checking can actually calling out those behaviors, and also if we actually hoping to use conformance checking as a tool to improving basically our current specular agents. I hope we are going to advance into this era called system intelligence. Basically the model is super good. They can actually understand everything and actually be able to create a perfect TLA plus spec. And there are a lot of efforts in doing that. Happy to talk if you're interested. But right now if we want to use some of the commodity out of box models, I think one way we can actually do it is try to leverage its coding ability, right? Because its coding ability is very, very strong. As we have seen, some of the tricks we use is that we try to turn the problem a little bit into the code translation problem. That's how we're able to beat some of the state-of-the-art models. Also one thing we all realize kind of observe is that the models they are doing okay on safety properties, but they are doing very poorly on liveness properties. It seems that the model really have trouble in temporal reasoning. Last but not least, this is some of the work we really are currently doing. Needless to say that we're continuously improving the specular's ability, right? One thing we are thinking about is actually combine a different approach. Ivan is actually in the call he did tons of work on the trace basic validation and using trace to basically enhancing the models, and that's something we really want to try. Chen and Emily I think they are very determined in using this TLA AI generated TLA spec to actually find the bugs, right? That's actually we can prove that those specifications are actually useful, at least help us to know that why they are not useful in finding real world bugs. One thing we have been constantly talking is that if we actually want to involve in this tool as a useful tool with the better figuring out or at least thinking through what is actually the maintainability of AI generated TLA specifications, right? For example, as there was a slide which talking about, do we really even need incremental manageability, maintainability, or we can always starting from scratch if it's good. So last but not least, we are continually hoping to build this tool, and right now it's a tool for ourselves. We're actually constantly using it, but we hope to make the tool useful for everyone in the community. So if you have any feedback, if you want any features, that would be highly appreciated and help us to making progress. That's all we actually prepared. I think if you have any questions, like, we would love to, like, discuss.
Yeah, okay, thanks a lot. That sounds really cool. Questions? Marcus, you have your hand up. Go ahead.
I have a couple of questions here. Maybe it was slide 14 or 13. You said Qian, you said that you run TLC for 10 seconds. What mode do you run it in? Is it like exhaustive or is it simulation?
Model checking.
Okay.
In
And
general, I will used to run for at least 1 hour.
mhm. Have you considered like perhaps doing both model checking and simulation? So that gives you like breadth, but also depth for some traces.
Yeah, in our benchmark Sysmo bench, we use both model checking and simulation to get more useful information. And in the future, I believe we will use both approach.
Okay. And then another question, perhaps I missed it. So you showed the instrumentation of the implementation. Was that done?
Yeah.
Was that also done by the LLM or was it done manually?
We have a instrumentation template, and for now, currently the template is write manually, but the inserting of the instrumentation is automated.
Mm-hmm.
Yeah.
So I think like this trace validation thing is a very tricky thing to get right, and it's likely, my experience is that it's likely to be specific to the system you want to check, right? So basically, different systems like have their own like trace validation framework. For example, like Ivan's Pico system had a very different trace validation like basically stuff. So my like basically thinking is like in a different system will have their different trace validation framework. So like it's very difficult like say like hey like let's just complete changing it into a unified way. So like with that like as a foundation, like the thing like we need to do like in the Specula work is that how can we actually map like basically a different like kind of trace validation framework into some unified like basically way for like Specula to making progress, to actually taking that to do that. So like this like first of all need like to write some drivers. The drivers like basically like the templates Chen was talking about. It's actually handwritten for the specific like basically system like the format like trace format. But when we have that, like the next challenge is that like because like the AI is keep generating the different like TLA specification, right? So like there will be need mapping like to map like basically the like that particular TLA specification generated like by the Specula like our AI models to like kind of the one like which actually match the template. And that mapping right now, like is done by the by AI, like or like by like the agent, not like handwritten, because otherwise that's too much in the benchmark. We actually check like, a little bit about we check a little bit about the mapping like kind of validity by hand during the paper writing, and it's actually doing quite well like in that mapping.
A related question, I mean, when you do trace validation, obviously, okay, you have to instrument the code and then you can collect traces. Now the next problem is to stimulate the system so that you get actually interesting traces out. And have you considered like combining, like, yeah, you instrument the code, you synthesize a specification, now you send it through Specula, and when you run TLC on it, you could, for example, collect coverage at the spec level and use that coverage to guide the stimulus for the implementation. Is that something that you have on your roadmap?
Yes, it is. And actually, there is a new Uppsala paper on such topics. So it's also inspired us, and we also plan to do such optimizations or new techniques.
Okay. Can you share the link to the paper that you just mentioned?
Okay.
Or the name?
Yeah. Let me paste the name a few minutes later.
That's the
Okay,
work
sure,
by
thanks.
Rupak Majumdar and co-authors, or is it a different paper?
No, oh, I found the paper, Model Guided Fuzzing of Distributed Systems.
Mhm.
Let me
Okay.
paste the name to the chat box. Yeah.
I think it might be Rupak's paper indeed. One question for the community, for you guys, that would be very useful to us is, I mean, kind of like twofold. One is like, what else would you use these kinds of specs for besides bug finding? Because clearly to us, a bug is like an indication of value that we can demonstrate, right, from an AI generated spec. But is there other uses where this could be, where you could plug in a spec, And maybe a second question is like, what would give you confidence in this kind of spec? Because clearly we can do, trace validation, and it's kind of a pay-as-you-go thing. As the more traces you have, the more validation you have, the more confidence you have in a spec. But maybe there's no amount of trace validation that would convince some of you that this spec is actually appropriate. And so I'm kind of wondering about both, right? Like, what would give you more confidence, and also, where would you use this kind of thing? So, Marcus, you have your hand up.
Unless somebody else wants to go first. Otherwise, I think I'm going to sort of answer with a counter question. How human readable are those specifications? Because where I'm coming from is, well, in my company, we have to provide lots and lots of documentation about systems, and connecting documentation to implementations is super hard, right? And that's one thing we use TLA Plus for, and especially TLA Plus is well suited because it has refinement. So I'm wondering if even if these specifications are not necessarily superhuman readable, the next step could be to take that specification, synthesize a more high-level specification, either with an AI or by a human, and then show that the high-level specification is refined by the synthesized specification, and the high-level specification then becomes part of the actual documentation. So that seems pretty useful to me. Essentially, yeah, in broad strokes, connecting high-level documentation to the actual implementations, which right now in the industry is essentially done manually by review. There are no guarantees whatsoever. So what you just said about, okay, you can do trace validation forever, but never get really guarantees. I mean, the state of the art in the industry is review, and then things like MCDC coverage. You show that your tests cover all your branches. So that's what we're comparing to, which is not super strong.
Yeah, I mean, in terms of readability, you saw the spec that Chung was demonstrating. I think a lot of it depends on the readability of a code, of the source code. So, because a lot of the identifiers and names and modularity really comes from the source code due to this kind of translation strategy.
Yeah.
And so I think it's quite readable for the person who wrote the code, maybe not readable for an outsider. That would be
Yeah.
perhaps the right answer.
Quick follow-up question. So far, it seems you only feed the implementation into the pipeline, into Specula. But there also tends to be existing documentation, right? Do you leverage that?
Can go ahead.
Since I think this is for me, this is really another question. Currently, I just want to focusing code to specification, and maybe in the future I will try some document to specification, the workflow design. And we need to figure out whether feeding documentation will improve the maybe agent or large language models performance. I think that's the interesting direction.
Yeah, I think it requires a bit of expertise to figure out what part of the doc to give. And we haven't, it's difficult to assess essentially that free variable. So we've been kind of leaving it out. But I think it's a really great idea.
So coming back to what Marcus just asked about I mean, you mentioned these multi-grain specifications, or however you call them. So where you have specifications basically at different levels of abstraction. So how are these? Where do these come from? Because what you showed, as far as I understood, was the low-level specification that corresponds to the code. So are the other specs?
I use that as a motivation. Like it's not like done by the Specula tool at all. We hope to get there, but that's like because like we are writing so many specifications. I mean, the students are writing so many specifications. That's like basically kind of motivate us like to generating it like using AI automatically. But it's not like in the Specula tool yet.
To answer Ivan's question, I think trace validation is, yeah, probably like a killer application for this. Just because we don't really have a good story now of how to easily go from a TLA plus specification to like trace validating an existing artifact. I mean, the only thing I could think of would be generating like more abstract specs and getting refinement working, but that sounds very hard. That's like even harder than a regular temporal property generation. But yeah.
Yeah, on temporal properties and liveness. So that also reflects my observation that yeah, temporal logic seems to be not just difficult for humans, but also difficult for AIs. Yeah, no wonder. On some level, I think this is like crucial, right? Okay, you get some guarantee that your specification is live from doing trace validation. Because if the specification is not live, then that trace wouldn't be able to be conformance checked. But beyond that, how do you essentially right now just have the human write the liveness properties and then check those at the spec level? Or what do you do about that?
Yeah, we just write the properties and the invariants manually. Since we think generate invariants and or properties is another question, which is different from generate maybe TLA plus model for system implementation. Not only Swiss Bench but also Specula, both use such invariants and property written manually. So in our next step is to get a as high as high quality specification, and we can check the specification using such a manually written invariants to try to find bugs in real world system. That's our plan.
Yeah,
Next
like
step.
the specification is a very overloaded term, right? Like we currently mainly focus on the model, not the environments. That's like what's our current focus. There are actually quite some work, like if you search online, like they try to generate the environments or like assertions, like when they're talking about test cases. And like I think like some of them do apply, partially because like if you think about like the model we're generating, right? It's kind of a model like which describes the systems, not only the protocols but also the systems. So like you can imagine like basically taking some of the assertions like in the test cases, and then like basically like turn them into some environments like for the code. But again, like we haven't done anything there yet. Probably like the first step is actually to get the model correct. So all the stuff like all the environments, no matter safety or liveness, like basically right now is actually handwritten into templates.
Yeah, that resonates with my observations. The problem is that the invariants and the liveness properties, they're never in the current software development lifecycle, they are never actually formalized, right? You have assertions and tests, yes, but nothing beyond that. And even if you look at documentations, they're nowhere spelled out explicitly. So I have to read in between those lines, right? Which is perhaps another thing you can use AI for. Summarize the documentation in search of invariants. I think what's helping here is that the invariance and temporal properties in TLA plus are pretty concise, so human review is feasible.
Can I ask a couple of questions? Can you hear me?
Yes.
Yes.
Oh, okay, great. I'm just heading to many microphones. So I didn't exactly get how to make sure that the specification doesn't miss any behavior, because my experience this Claude is something like I tell it to do something and then it partially implements it and then says to do blah blah blah. And how do you make sure that it doesn't happen basically?
Chen, do you want to take that question?
Oh, to be honest, we are just improve it, but you just large language model is a black box, and we can't promise that it won't make any mistakes. We use many techniques like draft base. We will first generate a draft base using a natural language, which is close to the training data of large language models. And we will use a retrieval argument generation process, which can correct the errors exist more efficiently.
Chen, I think the
And
question
finally,
is that, Chen, I think the question is that what if we miss some components? You generate everything correctly, but there's some missing components you didn't generate.
Yeah.
And in that case, you can verify everything, right? But whether there's a guarantee, I don't think we have a guarantee. Even we do all the RAG and all this stuff, it only proves that what we generated is correct. But it doesn't prove that we generate everything. There is no completeness guarantee. So that's probably is the answer. Of course, if you really missing some major components, you won't even be able to pass the trace validation and all these things. But if you're asking a guarantee, there's not there yet.
Yeah, I think trace validation, I mean, you're gonna have to make a bunch of assumptions like the trace actually covers the code, and that code at least observe, has the same behavior observationally, right? And it depends at the level at which you're doing trace validation. So is it at state or some other kind of thing? So you're gonna have to it's gonna have to be defined relative to that procedure basically, and only for that one path, So I think that's the only real thing we'll guarantee in the end, I think, relative to the input code.
Yeah, I guess you need some kind of coverage. I'm not sure would it be in this case, but something like that, right? At least that you cover all functions, whatever, transactions, whatever you call them, is your specification.
Yeah, we plan to do coverage to add coverage metric since we are using a translation process, and there are one-to-one mapping between the functions in code and actions in specification. So we can use some code coverage, maybe for coverage for each statement, and mapping to the maybe expressions in specification. We plan to do this. Yeah.
Probably some static analysis. I mean, this is not directly answering a question, but you can kind of show that, the state matches one-to-one, the decomposition, for every function, there's an action. For every branch, there's an equal branch on the other side. So you kind of match the skeleton in a static analysis kind of sense between the two. But it's not going to tell you that functionally they're doing the same thing.
Yeah, I mean, it's a hard problem. I'm not saying it's easy to solve. And another question I had actually, I'm surprised Stefan didn't ask it. Did you consider generating proofs until APS for these specifications? It's also a vast topic. I'm not saying that it's easy. But I know that lean people are trying to do that, so why not do it for TLA?
Folks in Rockcock are doing that as well. Like a lot of folks are working on this domain. Yeah, I think the difficulty I think we're just much more systemsy in our approach. We're systems people, so we're much more interested in finding bugs rather than proving things correct. And so I think that's our bias, I would say. I think also for proofs, for the size of systems that we're talking about, they're just enormous. And so yeah, it's like the amount
Yeah.
of the
Actually,
amount of
actually, for formal method guys around me, more are doing formal proofs than the guys doing model checking.
To me, perhaps the generated specification, that's a one-to-one mapping to the code, is maybe too low level to approach a proof. I would imagine that you would abstract that one into a more high-level specification. And then,
Yeah.
try and synthesize the proof for that. And then I guess it boils down again to where do you get the invariance from, the liveness properties from that you want to prove.
Yeah, makes sense.
I think there's
But
kind
since
of space for refinement,
Right.
like something that, Jinyan was talking about is these multi-grain specifications. And I think if we can find a way to have abstraction that's reliable, I think that'll open a lot of, different venues for proof techniques down the line. So that's kind of like an exciting large dimension that we haven't ventured into, because right now we're just like, how do we generate a thing that that is somewhat plausible? But once we get refinement in place, I think that would be the right place to plug it in.
Right. Which I guess is also among the harder problems, right? I mean, people call it the art of refinement or the art of abstraction. So that's a harder problem for the LLMs as well as for the humans.
Well, there's also the art of writing specs, and we're starting to generate them automatically. So
Okay, I'm afraid we are running out of time. So unless there's a really urgent question or comment, or somebody wants to, so we couldn't do the round table. If somebody wants to mention something that's really important and shouldn't wait until next month, then please speak up.
And one admin question here. So these talks usually are published on YouTube. Is that fine that this presentation goes to YouTube?
Yes, I think it's
Yeah,
fine.
that's fine.
It's okay.
Okay.
Yeah.
Thanks. Okay, it was a great
Thank you.
presentation.
Thank you for having
It was great
us.
to have you.
thank you for having us.
Yes.
See
Yeah.
you. See you.
See ya.
Bye.
See you.
Have a good day, night, whatever it is where you are.
Yeah, see you.
Bye bye.
Bye bye.